so I will next introduce the next speaker. Next speaker is Stuart Russell from the University of California at Berkeley, where he's a professor and where he was head of department. He holds the Smith-Zadeh Chair in Engineering. And most important for us today is a founding director of the Center for Human Compatible AI, first of its kind center, which has, I think, inspired a lot of centers around the world now. And we know Stuart for a long time. He's been visiting us in Paris 12 years ago, and he comes back regularly. And he was last here in this room 5 years ago to present his the new book, Human Compatible, which is really one of the main books on this field we explore today about probably safe and beneficial AI. And also Stuart is very famous for his scientific contribution to the field of AI, and most AI researchers know also his textbooks written almost 30 years ago, the first edition now. And I'm always very impressed by the numbers, translated in 14 languages, used in over 1,400 universities around the world and 828 countries. I think we are missing. It would be very nice to have the number of people who have used it, not as a lecturer, but as a students, and to measure the percentage of AI researchers in the world who have actually studied with your book. But yeah, today is not this book is not the topic of today. So we're going to listen to Stuart talking to us. Especially, I think it interests everybody, but especially people involved in AI research. What if we succeed? And maybe it's not something that most researchers in all sciences think about enough. But I think in AI, like in nuclear physics and maybe biology, I think it's a very important question we should think about together. But Stuart has been thinking about it for at least 10 years since he visited Paris, I think 12 years ago. So please welcome Stuart.
And as Vincent mentioned, actually, a lot of the ideas I'm going to talk about originated during a sabbatical that I took here at Leipzig in 2012 to 2014. Actually, specifically on the metro, on the way to a rehearsal at the Orchestre Lemure. All right, so here are a few principles that I think we need to abide by. So, first of all, we have to think about what's coming down the pipe. That thinking about safety and how to regulate the systems we have now doesn't make any sense, right? I mean, imagine if we had done all our thinking and all our regulations 3 years ago, before large language models became a thing. Everything we would have done if we hadn't been forward thinking would have been more or less a waste of time. And to some extent that happened with the European Union AI Act, which had to add a whole section to deal with large language models which emerged during the development of the Act itself. So if we have to plan for AI systems that exceed human capabilities, then, as Joshua mentioned, I'm in favor of humans remaining in control of our own civilization. Not everyone is, but I'm guessing if we took a vote in the room, I think most people here would be in favor of humans remaining in control. And so you put those two things together, the only option we have, besides not having any AI at all, is having AI that we can guarantee is safe, that we have mathematical guarantees. Because what is a mathematical guarantee? It says there isn't a possible world where humans go extinct as a result of AI. if you can't establish a mathematical guarantee, that means there is a possible world in which humans go extinct as a result of AI. And eventually, that possible world will come to pass. And the language that we've been using up to now is at best talking about making AI safe. And if you unpack making AI safe, what that means is you make AI and then you think about how to make it safe. And in my view, this is a non-viable approach for reasons that will become clear. Instead, we need to make safe AI that is safe from the beginning by design. And I also want to point out that we're not just talking about existential risk here. The problem is that we don't know how to make AI systems that don't harm people. And some of those harms are happening now, and some of them will be happening within the next 18 months, and some of them are further down the road. But the same issue is there in all of these harms. It's a consequence of not knowing what we're doing, not knowing how to do the engineering and the design, and not knowing how to establish those guarantees. And the reason we can't make AI safe, in other words, we can't make AI and then make it safe, is because of a principle that I describe in the book. It's a very simple idea, and it's easiest to understand in the context of taxes. So we've been trying to make tax law for more than 6,000 years. And it doesn't work. I think the tax code in the US is up to 72,000 pages now. I'm not sure what it is in France, but it doesn't work. And why is that? It's because people don't want to pay their taxes. And so the only way we're going to get AI systems to behave themselves is basically if they want to pay their taxes. So that has to be designed in from the beginning. You're not going to get a system that wants to avoid taxes to pay its taxes if it's more intelligent than you are. If it's, to continue the analogy, right, if its lawyers are much more expensive than the lawyers who work for the government. So these are some basic principles I think that we have to keep in mind through all the work that we do. This is very annoying still. Okay. So if we follow all these principles, AI as a field is going to be much less sexy. It's going to be the whole idea that we're going to move fast and break things, which is the Silicon Valley mantra, that's not going to work anymore. It's going to be more like aviation and more like nuclear power. And just to give you a sense of how seriously people in nuclear power take safety, one of my colleagues, Ed Morse, did a simple calculation. So on the x-axis, he plotted the mass of the nuclear power station. Literally, how much did the nuclear power station weigh? On the y-axis, he plotted the amount of paperwork that was generated to show that the system complied with the safety regulations. And it's pretty much linear. So the heavier the nuclear power station, the more paperwork there is. And what is the gradient, right? What's the slope of this line? 7 kilograms of paper per kilogram of nuclear power station. So in comparison, I would say, AI safety is not even a gram of paper per kilogram of AI system. right? We do not take it seriously. Other fields take it seriously because I guess they care, and because governments have required them to care. Okay, so I'm going to briefly introduce the way that we have thought about AI. Later on, I'll explain that we're not quite doing this anymore. But for most of the history of AI, what we've done is to build machines whose actions can be expected to achieve their objectives. So this notion of intelligence was borrowed from economics and philosophy in the 1940s, and it dominated almost all of the research that took place in AI. So, for example, when we train AlphaGo, we define the objective of winning the game, and AlphaGo learns to achieve the objective. When you navigate to a destination using your phone, the phone is given the objective of finding a route to that destination, and then the algorithm figures out the best way to get there. And something people are doing now is designing automated corporations where you just set up an agentic AI on the web and ask it to maximize shareholder return. So all these are objectives, and this mode of designing systems is very powerful in general. So control theory, for example, which runs chemical plants and aeroplanes and so on, is based on defining objectives. They call them cost functions, and then minimizing the cost for deviations from the ideal behavior. Okay. So AI is actually much more ambitious than control theory or statistics or economics or operations research, all of which follow this general model. Because we want general purpose AI systems that match or exceed human capabilities in every relevant area. And the first question you might ask is, well, do we have this general purpose AI? 5 years ago, no one would have a slide with this question, but now it's a serious topic of debate. In fact, my co-author on the textbook, Peter Norvig, wrote a paper saying we have succeeded, that we do have general purpose AI in the same sense that the Wright brothers had an airplane. And the Wright brothers in 1903, their airplane wasn't very big, and the seats weren't very comfortable, and the drink service wasn't that great. But those are things that we fixed with ordinary engineering, right? They had the basic idea, they had an airplane. And so Peter Norvig's argument is we have general purpose AI in the form of systems like GPT-4, and it's just a matter of improving the seats and the drinks. I disagree. I think there are fundamental principles that we have yet to discover. And because we haven't really discovered those principles and those methods, the AI systems are actually not as intelligent as we need, and probably not as intelligent as we think. They are doing something. There's no question that what's happening in GPT-4 and Gemini and others is interesting, and it exhibits capabilities that we wouldn't expect a language model. You know, we've had language models for more than 100 years, and it's only when they got very, very big that they started to exhibit interesting kinds of behavior that don't look like just generating text. They look like reasoning, problem solving, extrapolation, analogy. The thing is, we don't know how any of it works. So we have made a practical advance based on an unknown scientific principle. Usually it's the other way around, right? So for example, radio, we didn't just discover radio and then try and figure out how it worked, right? We figured out the scientific principles of electromagnetic waves, and then we made it on that principle. But here we've done it the other way around. We've got something that works, but we don't know how or why it works. And so until we figure that out, we don't know how to put it together with other principles to make more powerful systems. We don't know what's missing. We don't really know what to do next. In fact, the only thing we're doing next is trying to make it bigger and hoping that more things will happen. So I'm going to try to convince you actually that we don't have all the answers. And with all due respect to my colleague Joshua, who was one of the main contributors to developing deep learning, at least the feed-forward circuits that constitute large language models have a very simple property, which is actually good, which is that the amount of computation that takes place from input to output is just the size of the circuit, because the signal comes in one end, propagates through the circuit, comes out the other end with the answer. And so the computation is proportional to the size of the circuit. But there are a lot of computational problems, as we know, that can't be solved in linear time. For example, a whole class of NP hard tasks require exponential time in the size of the input layer of the circuit. So that means if you're going to train a circuit that can solve these problems, the circuit is going to have to be extremely large. It's going to have to be exponentially large in the size of the input layer. And so if you have a very large circuit, that means you're going to require an enormous amount of data to train it. So this approach to generating intelligence, where all of the deliberation happens almost instantaneously, meaning the system can't sit there and think about what to do, right, or what the answer is. To train such a system requires very, very large amounts of data, and that's exactly what we're seeing. It also means that the circuit is not learning the concise representation of many of the concepts that we would like it to learn. And in fact, it's learning sort of piecemeal approximations. Some people even argue that they're little more than glorified lookup tables. So let's see what happens, right? We all know that AlphaGo defeated the human world champion, and this was China's Sputnik moment. This is what convinced the Chinese government to invest hundreds of billions of dollars to achieve AI supremacy. But some of my students and I suspected that actually AlphaGo did not understand the basic concepts of Go correctly. One of the basic concepts of Go is a group of stones. So stones are in a group if they're connected to each other vertically or horizontally on the Go board. And if the system doesn't really understand the concept of group correctly, then you can find situations where the program is going to make horrible mistakes, because that's the fundamental concept of the game. And this turned out to be the case. So we're going to play one of the superhuman Go programs. So in 2017, they were about as good as the best human player with a rating of about 3,800. The best programs now are in the CataGo family and some other families where they're rated around 5,200. So they are massively superhuman. And I'm going to show you a game between the massively superhuman CataGo and a grad student actually at Montreal, where Joshua is, Kellen Pellerine. He's a good amateur player with a rating of about 2,300. So he is massively less good than the human champion, and the human champion is massively less good than CataGo. And we're going to give CataGo a 9-stone handicap, meaning that CataGo starts with 9 stones on the board already. Okay? Which is the kind of handicap you give to a 5-year-old who's learning to play the game. So this is a huge insult to Kata-Go. Okay, so if you don't play Go, I'll explain very quickly how it goes. You put stones on the board, you take turns, either black or white stones. You try to surround territory with your stones, and you try to surround your opponent's stones with your stones. If you surround a group of your opponent's stones completely, meaning they have no spaces adjacent to them at all, then those stones are captured and removed from the board. Okay, so now you know how to play Go. We can enjoy the game. And so keep an eye on what's happening in the bottom right quadrant of the board. So right now, white is starting to make a little group in a circle, and then black, the computer, is surrounding that group to stop it from growing. And now white, Kellen Pellerine, is surrounding the black group. And black has many, many opportunities to rescue that group, to connect it up to the rest of the board, but doesn't seem to understand that its group is going to be captured. So it does nothing and allows Kellen to capture that group and kill it. So then Kata-Go loses the game. And this happened 15 times in a row. And it also happened with all the other leading Go programs. So the evidence is clear that the Go programs have not correctly understood this basic concept of what is a group of stones. And this particular kind of group, which is a circular group, it doesn't seem to recognize as a group somehow. So we then trained it to recognize this kind of group specifically to avoid this failure. And then we found that it doesn't recognize figure of 8 groups. And so you can get it to lose all its pieces by making figure of 8 groups. So there's something fundamentally wrong with the ability of these kinds of systems to learn basic concepts from a practical number of examples. And I think this will actually limit the results of scaling up large language models to bigger and bigger and bigger models. So this question is important, right? Will we succeed? And many leading experts, actually people who have a lot more experience than I do working with these systems every day, predict that this is going to happen before 2030. So in fact, Dario Amodei just the other day, he's the CEO of Anthropic, predicted 2026, which is not that far away. So Leopold Aschenbrenner, who produced this graph, predicts 2027. I've heard Demis Hassabis talk about within 2 or 3 years, and that was a year ago. So these are not to be dismissed. These are serious people who have serious amounts of experience with these systems. It's also worth noting that the budget going into the development of AGI is enormous. It's probably, on an annual basis, 10 times bigger than the Manhattan Project that produced the first nuclear weapons. It's 100 times bigger than the annual budget that went into the Large Hadron Collider, which is the biggest scientific instrument we've ever built. And by some measures, this might be the biggest single capital expenditure in the history of the human race. So we can't dismiss it. We can't just say, it's science fiction, the idea that AGI will happen. That's just science fiction, as I've heard a lot of people say. And even though I've given some arguments saying that simply scaling up a feed-forward circuit is not the answer, they are already aware of that, and they are already trying lots of other ideas. In fact, GPT-4o1, which was just released, a system that does reasoning, is precisely trying to get around that by allowing it to do more computation, by actually calling itself many times and doing individual reasoning steps and chaining those together. On the other hand, if if I'm right in saying that deep learning per se isn't enough, right? So to learn these concepts correctly, to generalize properly from examples, then we do need different ideas. It's also the case that I don't think we have enough data to train a model that's 10 times bigger than GPT-4. There literally isn't enough text in the universe. Some people argue we can get around that by just generating text from the model and then training on it. I see some of you smile like, yeah, that's obviously stupid, right? And in fact, there are some recent papers showing that it is stupid, right? So mathematically, you can show it's stupid. But, don't forget that AlphaGo is trained only on artificially generated data, right? There were no human games, I should say in the latest version, Alpha 0, there are no human games there. All of its data is artificially generated. So it's not completely obvious that it cannot be done that way. But another thing that might happen is an AI winter. So I actually joined Berkeley in 1986, shortly before the first big AI winter happened. And by 1990, my AI class was down to 25 students. It's now about 1,000 or so. Right. So that collapse can happen very, very quickly. And if the promises being made do not come to pass, do not deliver the returns that the people who are investing on the order of $1 trillion expect, then the winter could be very, very severe. And it might be another decade before people are even interested in the subject of AI. So we have a variable timeline, right? Some people say 2026, maybe it's going to be 2036 or 2040, but it's going to happen. And the upside, what is the reason, as Joshua mentioned, the reason is that if you have general purpose AI, you can use it to do everything that human beings can do, by definition. And humans can create a civilization like the one that we enjoy in Paris, and we could deliver that standard of living to everyone. And that's about a 10-fold increase in the GDP of the world. And the net present value, so the cash equivalent of that, would be about $15 quadrillion. So that's the magnet that Joshua mentioned that is pulling us forward. There is a question about what we would do. So if AI systems are doing everything that human beings can do, then there's a question which Wall-E, the film, actually describes very well, right? That we become infantilized because we no longer need to know how our civilization operates. But I want to talk about the other consequence of success, right? The downside consequence that Alan Turing predicted when he said, at some stage, therefore, we should have to expect the machines to take control. And I think the question underlying that prediction was this one. How do we retain power over entities more powerful than us forever? Right? That is the question that we have to ask. And if we don't have an answer to it, we cannot proceed. So I'm being a little more forthright than Joshua. We cannot proceed. So how do we answer this question? Well, if we have no say in the design of the AI systems, if we don't understand how they work, then it's exactly as if those AI systems landed from outer space. And if AI systems that are superior to human intellects landed from outer space, then we're not going to retain power over them. End of story. So it has to come from our ability to design AI systems that have a desirable property. And the desirable property that we want is that no matter how intelligent the system is, it behaves in such a way that guarantees that we will be happy with the results. So how do you set up the problem that the AI system is supposed to be solving, right? It's sort of constitutional design, such that no matter how well it solves it, we're guaranteed to be happy with the result. And I'll give you two hints. Number one, it's not what we've been doing, namely optimizing a given objective. Because what we've found already is that as we move into the real world, optimizing fixed objectives fails, because the fixed objectives inevitably leave out stuff that we care about. They are misaligned with what we truly want the future to be like. It's also not what we're doing with large language models. So large language models actually have deviated from the standard model of AI in the sense that we don't even know what objective they're optimizing, because all we're doing is training them to imitate human behavior. And if you train them to imitate human behavior, then they're going to probably adopt human objectives on their own account. And if you think about the human objectives that went into generating the training data, they were things like, I want you to buy this thing from me. I want you to think that I'm authoritative and I know what I'm talking about. I want you to vote for me. I want to be the richest person on earth. I want you to marry me, right? These are all objectives that humans have, some of them reasonable, some of them not, but none of them are reasonable for AI systems to have. And yet we are training them to have those objectives. And we have no idea of which ones they actually are pursuing under what circumstances. So this is an even worse approach to AI than the standard model. So a direction, this is the subject of the book Human Compatible, right? To avoid this King Midas problem, the problem of misspecification of objectives, we can set up the mathematical problem as follows, that first of all, the AI systems have to act in the best interests of humans. That's their objective. But here, that objective is not spelled out. It's not directly observable to the system. Instead, the system is explicitly uncertain about what those human interests are. So the human interests become a latent variable, a hidden variable in this problem formulation.
Yeah.
And it's perfectly possible to take that formulation in English and turn it into a mathematically defined problem that we call an assistance game. So it's a game because it's a decision problem that involves two or more entities, at least one human and at least one machine. And it's an assistance game because the machine part of this game is supposed to be assisting the human in achieving whatever payoff function the human cares about. So the machine's payoff is whatever payoff the humans achieve, but the machine does not know initially what that payoff function is. This is a perfectly straightforward type of game, and we can actually solve these games, and we can look at how they behave. And as we might hope, they defer to the human participants in the game. They exhibit minimally invasive behavior, so they only change parts of the world where they're sure that that's what the humans want, and they don't mess with the rest. They ask permission before doing something that does mess with the rest. In the extreme case, they are willing to be switched off. And we can show mathematically that that willingness to be switched off, the incentive to allow humans to switch them off, comes directly from the uncertainty about what humans want. So this, I think, is the core of a way of building AI systems that are safe by design. And we can show that actually it's in our best interests, even if we don't know what our own best interests are, it's still in our best interest to build assistance game solvers because they will be helpful to us in achieving our interests. In fact, they may even help us find out what our own interests really are. So since I published the book, we've made some progress on solving these kinds of games. So we've extended in the book and the early papers, those assistance games were what we call fully observable, meaning that both the human and the machine could observe the complete state of the world. But in real life, we can't observe the complete state of the world. And if you were a kid and your parents asked you to clean up your bedroom, right, you presumably quickly learned that you could just shove everything under the bed and then pull the cover down and then tell your parents that you tidied up your bedroom, right? So that's a possible failure mode that you might get in a partially observable assistance game, right, where the AI system might fool the human into thinking that their interests were being pursued. But in fact, we can show that if you formulate this correctly, that doesn't happen. And even in partially observable case, the AI systems are still provably helpful to us. We started being able to scale these solvers up to relatively large decision problems. So, for example, helpers in Minecraft, where you can start building something in Minecraft and the AI system is watching you and gradually figuring out what it is you're building and then helping you and even communicating with you about what you want done in Minecraft. I'll briefly mention the fundamental theorem of AI because this is really important, not just for assistance game solvers, but for AI in general. The fundamental theorem of AI is referring to something that we took as an article of faith for most of the history of AI, which is that AI systems should know things. That knowing things is a fundamental capacity that you need in order to be really intelligent. That article of faith has actually been discarded in the last decade. And instead, you will hear people saying, oh, we don't need knowledge, we don't need reasoning, we just need end-to-end deep learning systems that learn the policy, right, that learn directly what to do. And for example, some of the self-driving car companies have claimed that the AI system doesn't need to know anything about pedestrians or traffic lights or speed or velocity or slipping on ice or any of that stuff. It just needs to learn an end-to-end policy from lots and lots and lots of training data. And this turns out to be false. And in fact, you do need to know things. And literally, there are classes of environments where knowing things gives you exponentially better sample complexity than trying to learn an end-to-end policy. So I think this is an important result about how we should think about the design of AI systems. And it's a pointer to how we might move forward to get past some of the obstacles that deep learning presents. So there's a lot of open problems, and I really welcome help on trying to solve some of these open problems. So one set of problems has to do with the fact that as we move into the real world, assistance game solvers need to learn and reason about the preference structures of real human beings. And we actually know very little about those. There are journals devoted to that question. There's a journal of well-being where people write papers about what constitutes human well-being. But those are really just humans writing to each other. And I checked, and none of them say that, for example, humans want to keep their left legs. Yeah. Because it's sort of obvious, of course, you want to keep your left leg. I don't need to write a journal paper to say so, right? But from the AI's point of view, the AI doesn't know that. And so we do need to make sure that AI systems know that people like their left legs, know that we probably prefer the sky to be blue rather than orange with green stripes, and lots of other things that human beings never bother to tell each other because we just take them as given. And And then another set of issues comes up in social choice theory. So how do you make decisions on behalf of multiple human beings? And moral philosophy has been struggling with some of those questions. For example, how do you include the preferences of people who don't yet exist, especially when your decisions could affect who is going to exist in future? And these are really important problems to solve. So I want to just talk a little bit about how we go about doing the thing on the right, the making safe AI. So assistance game solving is one part of it, but I think we also need to get away from giant black boxes as the way that we build AI systems. So building our AI systems on a transparent substrate that is semantically rigorous, where we can take each component and understand what it means, check whether it's true. And I think the most promising technology there is probabilistic programming languages. We also need greatly strengthened formal methods. So formal methods is the branch of computer science that deals with the verification and synthesis of provably correct software systems. And this is what we're after all. So we're going to be using formal methods. And that technology is increasingly capable, but we need to develop it a lot more. One of the most straightforward kinds of systems about which we can provide guarantees is what we call a formal oracle. So a formal oracle, is a system that takes input in the form of premises, so facts, and a question, and then does formal reasoning steps using that information, and then produces an answer. So this could be based on logic, and so mathematical theorem provers are an example of this, or it can be based on probability theory and probabilistic programming languages, and their associated inference engines are an example of this. And typically, we've had limited success with this technology because of the combinatorics of the reasoning process. So we have been able to verify reasonably large software systems. We've been able to check the proofs of fairly impressive mathematical theorems, in some cases to prove new mathematical theorems that we didn't know before. The idea here is that we can use any AI system to help control the reasoning process of the formal reasoning engine. So we can put an AGI inside this box, or an ASI, artificial superintelligence, but its only option is which reasoning step to do next. And this type of system, this formal oracle from the outside, is, I think, provably safe. There's still some work to do to show that, but this is a provably safe and enormously valuable type of software system, because it's not just proving mathematical theorems, which you might think of as something that only mathematicians care about, right? A mathematical theorem includes generating software, right? So you want a software system that runs the Paris metro and is completely correct and safe. It can just generate one for you. You want a design for a building that's 3 kilometers high and will resist an earthquake of magnitude 10. That's a mathematical answer that a theorem prover can generate. So this could be enormously economically valuable and a kind of safe AI technology. So you might think that the companies who are spending, on the order of $1 trillion developing AGI would have thought about some of this, but actually they're running away from safety as fast as they can. So the safety and the ethics groups in most of the large tech firms have been disbanded, and some of them are blowing the whistle and saying, actually, OpenAI, for example, is deliberately downplaying safety because they want to be first to create AGI. And I think there was a question before, what is the appropriate form of governance? And an answer that we've been developing in discussions between some scientists from the US and Europe and some scientists from China in a series of meetings that started last October is what we call red lines. And it comes from the observation that the boundary between safe and unsafe is quite hard to pin down. Unlike the case of an airplane where it's unsafe if it touches the ground when it's not supposed to, it's actually quite difficult to say what is unsafe and what is safe and where exactly the boundary lies. So what we can do instead is simply to demarcate some obviously unsafe and unacceptable behaviors. So these are way at the unsafe end, and they're very clearly defined, and we definitely don't want AI systems to do those things. It doesn't have to be exhaustive. It doesn't have to cover the whole territory of unsafe behaviors. It just has to be clearly defined and obviously unsafe. And then, as with airplanes and medicines and nuclear power stations, the onus of proof is on the developer to show that the system will not cross those red lines, to provide high confidence statements of safety. And what should those red lines be? Well, they should be well defined. Ideally, they should be automatically detectable so that we can immediately switch off a system that violates the red line. And it should be politically feasible. And this is really important because we're talking about an industry that has at its disposal $15 trillion of capital and does not want to be regulated at all. So some examples would be no self-replication, right? The AI systems must not make copies of themselves either directly or by retraining themselves by reassembling the training data and then creating new versions of themselves that way. They should not break into other computer systems. They should not advise on how to build biological weapons. These are all perfectly obviously unacceptable things, and I think very politically defensible. But the companies, as I said, are fighting against this kind of regulation because it would actually require them to do something other than just fill in some forms, right? So what they would like to do is to just fill in some forms to say, well, these are the steps I took, right? Rather than saying, no, these are the steps you have to take. And part of the problem is they don't know how to provide any high confidence statement about anything related to their systems. And the argument, I mean, I'm having this argument right now. In fact, tomorrow I will be in Dubai having this argument with the World Economic Forum AI Council, some of whose members are industry representatives. And their argument is, because we cannot comply with this requirement, you cannot impose this requirement. Now imagine if nuclear power plant operators said that, or pharmaceutical companies, or airlines. In fact, imagine if the airlines were running airplanes built from giant birds that they bred. They don't really understand how the bird works, but they found that if you breed bigger and bigger and bigger birds, eventually they exhibit passenger carrying capabilities. And sure, sometimes they eat the passengers and sometimes they drop them in the ocean, but it's way too hard to prove that these birds are safe. So we shouldn't have to, right? We shouldn't have to comply with a requirement for the proof of safety because we can't, right? This is not an acceptable argument, in my view. Okay. All right, I will wrap up. I think I'm going to skip this this part and just go to the closing slide, right? So AI has this enormous potential that creates this unstoppable momentum, and that momentum is currently taking us off a cliff. There are other directions we could take. There are other roads we can follow that don't lead off a cliff. I think it's possible we can take them. So I don't like P-doom, because P-doom is like talking about P of rain tomorrow, right? It's a forecasting, but actually this is not a forecasting problem. This is a decision problem. And we have got to face up to that decision fairly soon. So I think we can take a direction that leads to safety. But as the Wall-E slide indicates, coexistence is also hard. And that's the next big problem that we have to solve. Thank you.
Yeah.